as a corollary to the Bursas theorem, we proved that if omega is a convex domain and if gamma is a closed polygonal path in omega, then for any holomorphic function f on omega, integral of f over the closed polygonal path is 0. Now, by using the second fundamental theorem of calculus, a complex analog of the second fundamental theorem of calculus, which was proved in the last week, we can immediately conclude a version of Cauchy's theorem in the case of convex domains. So, let me start by, this is sometimes also called the local version of the Cauchy's theorem. So, Cauchy's theorem for convex domains. So, let omega be a convex open set and f from omega to C be holomorphic on omega. Then f has an antiderivative in omega. And if gamma is a closed rectifiable curve in omega, then integral of f over gamma is equal to 0. We don't have much to do here. The proof is basically a direct application of the Cauchy's theorem for polygonal paths. Let me recall the statement for you. It's stating the following. Suppose we have a convex domain, and if we consider a polygonal path which is closed, and if f is holomorphic on omega, then the integral of f over the polygonal path is 0. Now, if you go back to the previous week's lectures and look at the second fundamental theorem of calculus, the precise requirement for a function f to have an antiderivative is that its integral over polygonal paths is equal to 0. So, by the second fundamental theorem of calculus, we can directly conclude that f has an antiderivative. Since integral of f over sigma is equal to 0 for any closed polygonal path sigma in omega, we have, by the second fundamental theorem of calculus, complex analog, an explicit antiderivative. Capital F on omega. Now, the moment we have an antiderivative, we can now use the first fundamental theorem of calculus to conclude the second statement, which now I am going to underline. If gamma is a closed rectifiable curve, then integral of f over gamma is equal to 0. This follows if f, small f, has an explicit antiderivative on omega. By the first fundamental theorem of calculus, integral of f over gamma is equal to 0 for every rectifiable curve gamma since f has an explicit antiderivative. So, in particular, if we pick two curves gamma 0 and gamma 1 from z0 to z1, then integral of f over gamma 0 is going to be equal to the integral of f over gamma 1. By considering gamma 0 plus minus of gamma 1, we can conclude whatever I just said. Right, so let's go back to the statement here. Why was it mentioned that this is a Cauchy's theorem? The conclusion here is what we have in the second variant of Cauchy's theorem, which was stated in the previous lecture. And we in fact showed that Cauchy's theorem, which was stated initially, and the second variant are logically equivalent. So this is exactly telling us the Cauchy's theorem when omega is a convex domain. But then convex domains are very special. For example, disks, rectangles, all these, the interior of a rectangle, all these are convex domains, but they are very special. And we would like to prove now the more general statement of Cauchy's theorem. Let's get to proving Cauchy's theorem in the general setting. So, proof of Cauchy's theorem. So, let me recall Cauchy's theorem for you once more. Let omega be an open subset in the complex plane and f be a function on omega which is holomorphic. Let's consider two curves, gamma 0 and gamma 1, with the same initial point and the same terminal point, such that gamma 0 is homotopic to gamma, reparameterization of gamma 1. Let me write that down. Let gamma 0 from AB to omega and gamma 1, say from CD to omega, be rectifiable curves. As of now, we would like to speak about integral over these curves. So let's confine ourselves to rectifiable curves on omega from z0 to z1. This just means that the initial point of both gamma 0 and gamma 1 is z0, and the initial and the terminal point of gamma 0 and gamma 1 is z1. So suppose we have two such curves from z0 to z1 and such that gamma 0 is homotopic to a reparameterization of gamma 1, then the conclusion is that integral of f over gamma 0 is the same as the integral of f over gamma 1. I would like to point out that the second statement that we had given in the last lecture for the Cauchy's theorem for closed curves, for gamma 0 and gamma 1 closed curves which are homotopic as closed curves, the conclusion that integral of f over gamma 0 is equal to the integral of f over gamma 1, that follows from this particular statement. I will leave that as an exercise for you to really sit down and verify based on the exercises and properties of homotopy which we had given in the first lecture of this week. Right now, we will be proving this particular statement of Cauchy's theorem. So, let me recall the statement for you. If we have two curves gamma 0 and gamma 1 which are homotopic with fixed endpoints, how did I mention that? Homotopic with fixed endpoints. Then the integral of f over gamma 0 is the same as the integral of f over gamma 1. Let's give a proof of this statement. The first thing to note is that integral of f over gamma 1 is the same as integral of f over a reparameterization of gamma 1. Since the integral is invariant under reparameterization, we may assume that gamma 1 is also defined on AB. After linear homeomorphism from CD to AB, we can get hold of a reparameterization of gamma 1 defined on AB, and the integral of f over this reparameterization is the same as the integral f over gamma 1. So, we will just prove that, we just need to prove that the integral of f over gamma 0 is the same as the integral of f over this curve gamma, the reparameterization of gamma 1. So, we may as well start off with the curve gamma 1 as being defined on AB. Okay. The hypothesis tells us that there is a homotopy from gamma 0 to gamma 1. Let us give the homotopy a name, let H from 0 1 cross AB into omega be a homotopy with fixed endpoints from gamma 0 to gamma 1. So, in particular, H is a continuous function on 0 1 cross. We also know that 0 1 cross AB is a compact subset of R, and continuous functions take compact subsets to compact subsets. So, we have 0 1 cross AB is compact implies H of the image H of 0 1 cross AB is compact in omega. So, notice that H is a function into omega. So, this is going to be a compact subset of omega. Since H of 0 1 cross AB is compact, by let u1, u2 up to un be open subsets of omega such that uj bar is contained in omega and H of 0 1 cross AB is contained in the union, maybe contained in the union of uj, where j is from 1 to n. Why do we have open subsets of omega? The answer is that for every point on H of 0 1 cross AB, we have some epsilon such that the closure of being an interior point, we can get hold of an epsilon such that the closure of the disk of radius epsilon around H of s comma t for whatever point s and t we pick in 0 1 cross AB, that is contained in our given domain omega. Now, take the cover of the image by such domains, such disks, and by compactness we have a finite subcover. Call the elements in this subcover as u1, u2 up to un. That certainly satisfies the condition we have written. So, we have crucially used the fact that the image is a compact subset of omega here to conclude that there exists u1, u2 up to un which satisfies this condition. And now, let R be the Lebesgue number corresponding to this cover. Recall that Lebesgue number satisfies the property that if for any point in H of 0 1 cross AB, let us take say s comma t in 0 1 cross AB, then H of s comma t will be a point in the image, then the disk of radius r around H of s comma t will be contained in one of the ui's and hence contained in omega. That is the key thing we are going to conclude from this. So, let me just give this collection a name, Lebesgue number corresponding to script u. Then for any s comma t in 0 1 cross AB, the disk of radius r around H of s comma t is contained in omega. That is precisely what we have. It will be contained in some uj, which in particular is contained in omega. Now, let us use the compactness once more and notice that H being continuous on a compact set implies that it is uniformly continuous there. Since 0 1 cross AB is compact, we have crucially used the compactness here, as you can see. H is uniformly continuous. On 0, 1 cross AB, and hence there exists some delta, there exists delta positive such that H of S comma T minus H of S prime comma T prime, this is less than let's say R by 4 whenever mod of S minus S prime is less than delta and mod of T minus T prime is less than delta. So this is just rewriting the uniform continuity of H in terms of epsilons and deltas. Here epsilon is R by 4 and the delta is the corresponding delta. So we have now developed the setup on which we will be able to prove the Cauchy's theorem. Let's now take a partition of 0, 1 and AB such that its partition size is less than delta. Let's do that. Let 0 equal to S0 less than S1 less than say up to Sn equal to 1 be a partition of 0, 1 such that absolute value of Sj minus Sj minus 1, this is less than delta. Oh, maybe I shouldn't just put it this way. Let's call this P1 such that the partition size is less than delta. That's good enough. Similarly, let P2 A equal to T0 less than T1 less than up to say Tm equal to B be a partition of AB such that the partition size of P2 is less than delta. So we have picked a couple of partitions. So it's time to draw a picture to capture all that we have done. Suppose we have a domain and suppose we have a curve gamma 0 from say z0 to z1, and suppose we have a curve, this is gamma 0, and suppose we have another curve this is say gamma 1 from again z0 to they are not coming out well. Let's see. This is better. This is gamma 1 from again z0 to z1 such that it is homotopic, and we have picked partitions. So partitions will be of this type. So there will be at S1, I'll draw it with another color. Red is the curve at the stage of S1. So this is gamma S1. So this is just gamma S0 as you can notice. And this is just gamma Sn. And let's pick violet to capture say gamma S2 and so on. So we can have for each of these SIs, if you look at H of Sj comma T, that is gamma Sj, and that is captured by such curves. We also have a partition now of the interval AB, and how is that going to? So I'll just use orange here to capture the partitions here. So this is say T1 or rather gamma 0 of T1, this is gamma 0 of T2, gamma 0 of T3 and so on. Similarly, we have gamma S1 of T1, gamma S1 of T2 and so on. So we have partitioned our interval AB in this manner, and we are looking at the image. We are interested in the image here. Now that we have captured our partition in the image here. Let's try to see what can be done further. Let's get hold of a path. Let Cij denote the polygonal path gamma from h of Si Tj to h of Si Tj minus 1 to h of Si minus 1 Tj minus 1 to h of Si minus 1 to Tj to h of Si Tj. So let me just draw that as well for you. So as you can see, there are 4 straight lines in this polygonal path. Let me use a green to capture that. So this is our ij. We go along a straight line to h of Si Tj minus 1, and then we go along a straight line to h of Si minus 1 Tj minus 1, along a straight line to h of s of I minus 1 to Tj, and then back to h of Sj Si Tj. So this is the path that we have just defined. Okay, what is the speciality of this path? As you can see, I have just used the notation Cij to make the notation compact. The key thing to note is that the diameter of Cij, this is going to be less than, well, it's certainly less than R, because the partition size is less than delta, implies that each of these straight lines is going to be less than R by 4. Notice that our delta was picked so that the difference h of s minus st minus h of s prime t prime is less than R by 4 whenever the distance of s to s prime is less than delta and distance of t to t prime is less than delta. That this condition is satisfied has been ensured by the way partition has been picked. So Cij certainly has diameter less than R in this case, and because of that, hence Cij is contained in the disk of radius R around Sitj. But then, what do we know about the disk of radius R around Sitj? We in particular know that it is a convex subset. And by the Cauchy's theorem for the polygonal paths on convex sets, by Cauchy's theorem for polygonal paths on convex open sets, we have the integral of f along Cij is equal to 0. So good, because we have just proved that the integral of f over Cij is equal to 0 for each of these i's and j's. So notice that Cij is a polygonal path which consists of the 4 straight lines, and therefore the integral of f over the Cij's will be the sum of the integrals over these straight lines. Using this fact, we can prove that, it's an exercise for you to check this particular fact, the integral over both sum over 1 to n and j from 1 to m of integral of f over Cij, what will this be? Let's just go back to the figure. It's such a good exercise for you to sit and check this out. If you take this green color polygonal path, and if you pick the blue color polygonal path, which I am going to draw now, and if you take the sum of the integral of f over these two paths, the straight line which is encircled by yellow, the integral over these over this particular straight line cancels off each other, because one is going to be the reversal of the other, and when you add it up, the integral cancels off, and the integral will be over the polygonal path which is now being drawn in yellow. This is an exercise for you to sit down and convince yourself that when you take the sum of the integral of f of dz, f of z dz over the Cij's, this is going to be equal to the integral of f of z dz over the following curve C. Maybe I will write it here, where C is the polygonal path which is defined in the following manner. It's going to be h, okay, it is the polygonal path connecting h of 1 comma t m to h of 1 comma t m minus 1 all the way up to h of 1 comma t0 to h of 0 comma t1 and all the way back to h of 0 comma tm. Notice that we have used the fact that h is a homotopy with fixed endpoints very crucially to conclude this particular fact. We can now write C as the concatenation of two polygonal paths connecting z0 to z1, where z0 was the initial point of gamma 0 and z1 was the terminal point of gamma 0. Let's do that. C is equal to minus of gamma 1 plus gamma 2. Maybe gamma is not a good notation to use, minus of sigma 1 plus, where sigma 1 is a path from h of, okay, gamma, it's a polygonal path from 1 t0 all the way up to 1 tm, and sigma 2 is the polygonal path from 0 t0 all the way up to h of 0 comma tm. So if you notice, minus of sigma 1 is now a path from h of 1 comma tm, the polygonal path from h of 1 comma tm to h of 1 comma t0 by reversing the straight lines involved. Or let me just put a equivalence here, because this is just a reparameterization of this curve. So I should maybe write this. C is then reparameterization of minus of sigma 1 plus sigma 2. But that is good enough for us, because we are only interested in the integral of f over c. We are not per se interested in the curve C itself. An integral of f over c will be equal to integral of f over a reparameterization, which is minus of sigma 1, which the reparameterization which we are interested is the one corresponding to minus of sigma 1 plus sigma 2. And this, by the various properties of integral, is just integral of f of z dz over sigma 1, or rather sigma 2, minus the integral of f of z dz over sigma 1. Okay, so what have we established? We have established that integral over c of f of z dz is the sum of the integral over Cij's of f of z dz. But we have just noticed that the integral of f of z dz over Cij's are all 0, and therefore the sum is also going to be 0. So let me now note, since integral of f of z dz over Cij is equal to 0 for all I comma j, we have integral of f of z dz over C is 0, which implies that integral of f of z dz over sigma 1 is equal to the integral of f of z dz over sigma 2. So what have we finally established? Let's go back. We have still not proved our result. We have only established that if we look at the pink polygonal path which I am drawing right now, if you look at this particular polygonal path, that is going to be sigma 0, and the polygonal path which I am drawing here, that's going to be, this is going to be sigma 1. So what we have shown is that the integral of f over sigma 0 is the same as integral of f over sigma 1. We are only one step away from establishing what we want. We want to establish that integral of f over gamma 0 is the same as integral of f over gamma 1. We will just show that integral of f over sigma 0 is the same as integral of f over gamma 0. That's quite straightforward again, because we have already proved that when we are in a convex set, then if you consider gamma 0 and gamma 1 two paths from the same initial point to the same terminal point, then the integral of f over gamma over the first curve is the same as the integral of f over the second curve. Rather, what we will now do is that the restriction of gamma 0 to tj plus 1 is contained in dh of 0 tj comma r, because of the very choice of our partition. The deltas were picked in such a manner that it will be in fact contained in a disk of radius r by 4. In particular, it's contained in a disk of radius r. Similarly, gamma of h of 0 comma tj to h of 0 comma tj minus 1, the image of this is also contained in. So when I say is contained in, the image of this is contained in. That's what it means. So maybe I can write it that way, of tj minus tj plus 1 rather. This is contained in d of h0 tj, and this is also similarly contained of 0 comma 1. This is also contained in dh0 tj comma r. And we know that dh of 0 comma tj comma r, that's a disk of radius r around h of 0 comma tj, which in particular is a convex set. And therefore, by Cauchy's theorem on convex sets, which we just proved in the beginning of this lecture, integral of f over gamma 0 restricted to tj plus 1, this is equal to the integral of f of z dz of gamma h0 tj to h of 0 tj plus 1. Now notice that sigma 0 is the concatenation of these type of paths, and therefore integral of f over sigma 0, this is just equal to the integral of gamma h0 t0 to gamma h0 tm of f of z dz, which is the sum of integral gamma h0 tj to h0 tj plus 1 of f of z dz, where j is from 0 to m minus 1, and this is equal to the sum of integral f of z dz over gamma 0 restricted to tj plus 1, again j from 0 to m minus 1, and this is just equal to the integral of f of z dz over gamma 0 restricted to 0 t0 plus the concatenation of these curves tm minus 1 to tm, which in particular is equal to the integral of f of z dz over gamma 0. So we have just established that the integral of f of z dz over sigma 0 is the same as the integral of f of z dz over gamma 0. Similarly, we can establish that integral of f of z dz over sigma 1 is equal to the integral of f of z dz over sigma over gamma 1. And we have just seen that integral of f over sigma 0 is the same as integral of f over sigma 1. And therefore, we conclude that integral of f over gamma 0 is equal to the integral of f over gamma 1. With this, we conclude the proof of Cauchy's theorem. Cauchy's theorem is actually a very powerful tool in the following sense. We have only defined integral of a continuous function over rectifiable curves. We did not weaken the curves, the regularity of curves more than rectifiable curves when we define the integral. However, if you consider an arbitrary continuous curve in a given domain omega, and if we are to ask what can be the definition of integral of a holomorphic function over this curve gamma, then we can actually use the technique which we used to prove the Cauchy's theorem, break the interval of definition of the curve gamma into small pieces. Look at the polygonal path which connects the partitioned points, and then define the integral of f to be the integral over this polygonal path. Cauchy's theorem tells us that this definition will be well defined, because if you take any other polygonal path of this type which is homotopic to our given curve gamma, then it will be by equivalence of homotopy, it will be homotopic to any other the polygonal path which was used to define, and therefore the definition will be well defined. We already started this lecture by proving Cauchy's theorem in the case when omega was a convex domain, and that was crucially used to prove the general Cauchy's theorem. But let me note a statement for a very special class of domains called simply connected domains. An open set omega is said to be simply connected if every closed curve in omega is null homotopic. If every closed curve gamma at z0 is null homotopic. Recall that a closed curve is null homotopic if it can be homotope to a constant curve. Null homotopic to the constant curve at z0. Such domains are good because then we can say something about a special case of Cauchy's theorem for simply connected domains. Let omega be simply connected and f be a function holomorphic on omega, then integral of f over gamma is equal to 0 for every closed rectifiable curve gamma in omega. Notice that if it is closed, it can be homotope to the constant point, and by Cauchy's theorem we have integral of f over a constant curve is 0, and therefore integral of f over gamma is also equal to 0. The conclusion is quite straightforward. The second fundamental theorem of calculus can be used here to now say that hence every holomorphic function on a simply connected domain will have an explicit antiderivative.